Hi and welcome back to another episode of the Hidden Quantum Champions. Scaling quantum technology, scaling quantum computers is challenging for various different reasons, and I've been talking about this many times in other videos before. Think about ions where you have this linear ion traps and you add another ion. It becomes more and more difficult to keep these linear chains actually up and stable. If you're thinking about superconducting qubits, you have all of these different radio frequency lines or signal carrying lines that go down into your cryostat where the cooling power is super limited, and at some point you're reaching the point where you just can't scale any further because you're limited by the number of lines and the cooling power. You can build bigger cryostats, but again, at some point you might run into some limitation here. Now, what if there was a way to actually connect multiple of those units together? Then you could have a couple of those chips and they're sitting each in a different cryostat, and then you would connect them in a way that they could exchange quantum information with each other. What if you could have multiple of those ion traps and you would connect them in a way that they can exchange quantum information super fast with each other? You might not even have to have them at the same spot. They could also be at different places. So you could have something like a quantum internet that connects quantum computers with each other, so you can make a mutual beneficial use of multiple of these units, chain them together so they become even more powerful. And don't forget, quantum computers, they scale exponentially as you add qubits. So one qubit more and you double more or less the power of the overall computer. So that's why it's also so difficult to keep simulating them as the number of qubits is growing. Now, today's company, which is based in, I would say, one of the most interesting hubs for quantum technology in the US, which is in the city of Chicago, is called memQ, and they are working on exactly that problem. They're working on an interconnection, and not only that, also the software orchestration layer and the quantum memory that is needed for that, to actually build something like that, to build such an infrastructure where you can connect multiple quantum systems with each other. And who knows, maybe one day we even connect the superconducting system with an ion system, because some of them, like some of the algorithm might run better on one, another part might run better on the other one. This is not focus of today's video, but we are looking into memQ and how they actually build this connective technology. And with that, let's jump right into their website. So here we are on the website of memQ. You see it up here. It says connecting to the future. Government, research and technology industry leaders have brought quantum computing from the realm of science to the gateway of commercialization. The next step is to harness the power of different types of qubits through quantum connectivity, spanning multiple systems to solve our toughest compute problems. And then, we can learn more here. We see a couple of names in here, QEDC, for example, Quantonation. We've talked about some of these labels that you are seeing here in previous videos. If you haven't seen them, go check out the Hidden Quantum Champions playlist on our channel, where you can find all of these companies. Now, moving on. Blending quantum materials and optics science into the technology of tomorrow. The memQ team brings deep expertise in the key areas needed to develop quantum technologies into market realities. Built upon rich competency spanning quantum science and engineering, advanced material science and engineering, integrated photonics chip production, and high-performance computing, our team boasts the credentials and track record required to successfully deliver the industry's first extensible quantum network architecture. Embracing an extensible quantum network architecture, so here you see the different categories, the different products. It starts with the XDQC, assigning workload tasks across the network, so that's on the software side. Then we have the QNIC, so entangling metaqubits with light for connectivity over a range of distances. The quantum memory, and I guess we will talk a little bit later about why this is needed, right? So providing stability, control, and a path towards enhanced entanglement link fidelity through massive multiplexing, and then quantum control, so switching, routing, modulation, and control of the quantum channel that scales with the number of nodes and qubits. What do we have here? So quantum interface control allow the extraction of qubits from QPUs in the form of photons. Then memory modules provide the ability to hold and act upon qubits in memory state across the network. And then network control allows addressing of atoms through laser modulation through the network. Furthermore, so catalysts for quantum networking, the power of quantum connectivity, scale, resilience, and compatibility. So scale enabling a modular approach to qubit density with a system, a data center, or a network. Then resilience, providing entanglement states across distance to ensure fault tolerance of the quantum resource. And then compatibility, allowing modularity and resource sharing across the quantum network, regardless of QPU modality or location. There's also a video here which I will not go through now, and then here we see the news article. I'm recording this video in June of 2026. The latest news here is from April 2026, so I would say reasonably up to date. DARPA selects memQ to develop hardware and network-aware quantum compiler to enable quantum computing at scale. And I guess that goes along with this DARPA initiative that we've talked about in earlier videos as well. And then we see all of the different news articles down here. We can also reach out to them via this contact button. Now, the interesting part is, as per usual, of course, in the technology, right? So what is the technology that they are building? Let's dive a little bit into this. XQNA, an extensible quantum network architecture. Quantum system work radically different. This means they communicate differently too. So connecting quantum systems is about more than routing bits over a wire. And I guess we will learn in a moment why this is the case. So in this world, matter is changed to light. Atoms are linked and tangled across space and time, and an infinite number of possibilities must be measured and analyzed at the atomic level. Infinitesimal shifts in sound, light, or temperature bring noise that destroys the delicate atomic balance. Quantum communications must manage all of these variables at the subatomic level. And that's just the start. Now, quick step back. What do we mean by that, right? So we have this entanglement. I think that's kind of clear. We need to be able to create superpositions and entanglements to actually benefit from this quantum properties of our system, and we need to be able to build them across the whole chip or across the whole system if you have multiple chips. And that is, let's say, the core challenge. Why is it that challenging? Because we are operating at the quantum level. So quantum always means the smallest possible. And here, for example, if we are thinking about energy, so if we encode our information in an energy, for example, an electron excitation, like a state excitation, bringing an electron into a higher orbital state, then actually this is an energy, let's say an energetic way to encode quantum information. And of course, this is extremely prone to environmental effects, because now you could have some kind of disturbance, right? Some electrical instability in the electrical grid that is not properly filtered away, that creates a little bit of a shaking electrical environment, and suddenly the electron starts to decay or falls down, gets dragged down because it gets excited by an external electrical force. So it's very, very difficult. And on top of that, because of the non-cloning theorem, you cannot just create a safety copy and have two copies of this information sitting somewhere, because quantum information theory does not allow you to actually copy these states. So you can only always work on the original state, and this one is extremely, extremely sensitive to its environment just by the definition that it's a quantum state. So that's an inherent challenge, and there are many different approaches to solve that. Of course, you need to step up the game in terms of measurement and control electronics. You need to be able to also figure out if something's going wrong. So that's the whole branch of error correction algorithms. There's error mitigation, so learning about your systems and trying to mitigate these errors from actually happening, and so on and so forth. So there's a whole bunch of different aspects to that. You can also step up your game in if you're looking at solid state qubits and creating those qubits, removing disturbances from the qubit system, like charge noise and like noise in terms of particles diffusing around and all of that kind of stuff. So there are many different aspects that you can take into account to actually make sure that your system works clean, but still it remains a challenging task. And then, of course, that scales from the whole quantum information processing towards the memory, towards the the communication, the propagation of quantum information. So, as quantum processors are pushed to communicate across distances that evolve from the broad to the cluster and eventually the global level, noise variables become exponentially harder to control. And therein lies the need of an extensible quantum network architecture which unfolds layers of technology to address the expanding problems of scale. Again, quick step back. So as you know already from classical silicon technology, the distance at which you apply fibers becomes smaller and smaller, right? In the old days, you would only use a fiber connection to connect the different continents with each other. So there was this below the sea underground cable that has been put between basically the west coast of Europe and then the east coast of America to basically create this internet connection. That was a very early example of a fiber connection. But then the distances became shorter and shorter. At some point, the fiber connection was then spanned between different supercompute centers. Now we are at the stage where you can get a fiber that goes into your living room. So you get an internet connection that goes into your living room. And if you're looking at supercomputing centers, already all of the different like boards that have the chips on them, they are getting connected with these optical links, with these fiber technology, and potentially even between chips or on chips you will have these optical links. So basically little sources that are producing photons and little detectors that are detecting those photons, because of the fact that you can move much more information via these optical links than you can via a classical electrical, for example, copper cable. Now, this is the one aspect that you're seeing. So the technological side is developing very rapidly in the classical semiconductor technology, enabling to move photonic sources, so photon sources and detectors, even onto the chip level. Now, on the other side, let's look at the quantum side of things. So in the quantum world, we are actually looking to increase the distance that we can create those fiber connections on. Now, why is that? What is this about? So the main driver for that as of today is the whole aspect of quantum communication. Remember, the second quantum revolution, so the revolution that is about single quantum systems and using properties of single quantum systems, has three main pillars, which are the sensing, the communication, and the quantum computing. Now, the sensing is about making sensors that are using single quantum systems to sense something in a very sensitive way, again because of the quantum properties. The communication, though, is about using quantum theory, quantum physics, to make sure that our communication is safe, that we are not being eavesdropped, and that our communication stays well encrypted. And there's a whole lot of companies that are working on this right now. There's a whole lot of investment going into that. And currently what we are seeing is, if we are looking into these, let's say, photonic-based mechanisms to connect two sides to each other and make sure that nobody can eavesdrop between them, quantum key distribution, we are typically reaching distances of around 100 kilometers. So that is roughly the maximum distance that we can go so far. So you could have two quantum computers maybe that can communicate over such a long distance. There's also ideas and there's also ways to get actually quantum information up into space and then have it communicated in space. So you could have links on the ground, links in the space, and then communicate between different instances within space. That's also something that has been already shown by companies to work for quantum communication purposes. And that might also be interesting now as we talk about quantum computers talking to quantum computers in quantum information way. And then of course you need the memory, because let's say you are sending a photon from one computer to another. It takes a little time for this photon to travel to the other computer, and then it needs to be converted back into some information, quantum information that chip can process. That will take again some time. So it will actually take a little bit of time to entangle two different units with each other. And in order for this information not to get lost, you need to have this memory sitting on the other side. So basically on the, let's say, information emitting side for this entanglement process. But let's go back to the website. So here you see technology extensible quantum network architecture. Again, there's a video here, and then some call to action to contact them. So not too many details written on here. I guess we will find the details if we are looking deeper into the different resources. So exploring the frontiers of quantum networking. We are pushing the boundaries of what's possible, from fundamental breakthroughs to applied innovations in quantum communication and entanglement. And then here, I guess we find some articles. So scaling quantum networks, the advantage of distributed quantum computing. Our CTO, John Sullivan, has deep roots in Chicago Southworks site, a full stack simulation framework for distributed quantum processors with CUDA-Q. CUDA-Q is the NVIDIA language for quantum programming, right? Then you see memQ delivers integration of advanced quantum computing components with commercial Foundry. So scaling, basically showing that the technology can be scaled. And then McKinsey's Quantum Technology Monitor distilled the rise of quantum networking. Then there are also technical publications, so publications that go into technical journals. We see a lot of scanning electron micrographs here and transmission electron micrographs, I guess, that are showing some nanostructures that they have built, so monolithically integrated C-band quantum emitters on Foundry silicon photonics. C-band is very important to note here. C-band is the telecommunication band. What do we mean by band? That is a specific wavelength that is being used in today's fiber networks when you have supercomputers talking with each other, supercomputer centers exchanging information, or also the stuff that goes via generally telco lines is all in this C-band. So the fibers are optimized for this specific communication band. They have a low loss in this specific communication band, and everything is kind of set up for this. So this is a big thing if you can basically show that you can integrate the C-band quantum emitters on Foundry silicon. Foundry silicon, of course, because it means you can scale it pretty well, because there's an existing architecture, an existing foundry, silicon foundry, that can already do this. Then we see here optical and microstructure studies of erbium doped titanium oxide thin films on silicon, strontium titanide oxide, not sure, and sapphire, so different substrates that have positive optical properties that are useful for this kind of application. Can also go into the details of this if you are interested. Can also make an extra video. Isolation of individual ER, that's erbium, I guess, quantum emitters in Anastasi titanium oxide and on silicon photonics, and then a perspective on the pathway to a scalable quantum internet using rare earth ions. And that's, I guess, these erbium ions that were mentioned before. And you see those publications, they keep coming, 2025. And then end of 2025, the latest one, erbium quantum memory platform with long optical coherence via back-end of line deposition on Foundry fabricated photonics. And then again, down here, a way to contact them. I think that's roughly everything that we can learn in terms of the technology for now. And then, of course, the details can be read up in the resources that are linked here, but I think a lot of stuff is also still in a conceptual level. Let's quickly check out the company itself, right? So the power of quantum connectivity, it says, the quantum sector is seeing increasing velocity evidenced by recent technological breakthroughs from companies, including, and these are not the hidden champions, these are the well-known ones, right? AWS, so Amazon, Google, IBM, and Microsoft, among others. Building scale, resilience, and utility to quantum. So while the initial focus has been qubit density, which means how many qubits can we get onto a single chip, the next big problem will be how to network these systems to work together. Quantum computers can't just drop onto a classical network without collapsing the quantum state, or in other words, that which makes quantum quantum. So quick step back on this last sentence, because I think that is also important, and I hope that already came across, but let's be explicit on that again. A quantum computer, when you, let's say, measure at the end, when you are running your algorithm at the end, when you measure, we say you collapse the quantum state. Collapsing basically means you're measuring it. Measuring it means you can either get a 1 or a 0 out of a quantum bit. So whenever measured and whenever initialized, this quantum state, this qubit, is always either in the position 1 or 0. What happens in between is the quantum magic. This is this whole idea of entanglement and superposition where everything is probabilistic. But whenever you measure at the end, you get either a 1 or a 0. Of course, you might not always get the same thing. That's the probabilistic effect, right? So if I initiate my qubit at 0, at the quantum state 0, and then I run a specific gate, for example, if I have a spin qubit and 0 is spin down and 1 is spin up, and then I run a rotation gate where I flip the qubit into the exact middle between those two, then it will basically rotate around this middle plane here. And now if I measure, what happens is I collapse this. So it either flips into 1 or it flips the other way around into 0. So I can only get those two states at the end, but what happens in between is probabilistic, and it has to do with this entanglement and superposition. Now, why can't we use the classical network to connect quantum computers to each other? Because the classical network can only communicate ones and zeros because it's built for classical computers, so everything is either 1 or 0. We cannot connect in a meaningful way two quantum computers to each other if we have to collapse the state first. What does that mean? Well, in the moment where I trigger the measurement, even of just a single qubit, I basically manipulate the quantum state. I destroy part of the quantum state. So let's say you have 5 qubits, you entangle them all with each other, and you're measuring one of those qubits, and you know, okay, now it's 1, and then you think you can send this information to another qubit, to another quantum processor, and then can keep doing stuff with it. No, it's not the case, because you're losing this property of entanglement in that case once you do this measurement. So you really need to be able to transmit an information like a superposition or to transmit an information like an entanglement onto another system, and that's not possible just with what we are using today in terms of infrastructure, because it only communicates ones or zeros. Like technically the technology that is below that, so the photons that are being communicated, they are actually capable of both. So they could be used as quantum information, they could be used as classical information. That's more or less about the sources, the photon sources that we are using, and the detectors and how things are set up, also what fibers we are using. But in theory, for the quantum communication community, they have already shown that you can use classical fibers like C-band fibers that are used in communication today. In classical communication, they could work to also transmit quantum information, but then let's say, the rest of the infrastructure is missing. And that's what this is about. So quantum computers can't just drop onto a classical network without collapsing the quantum state, collapsing as in measuring, right? Or in other words, that which makes quantum quantum. Now back to the text. So at memQ, we've developed an extensible quantum network architecture that enables networked quantum channels between quantum processing units and enables the use cases of scaling quantum compute instances beyond a single chip, cooperative processing between systems, resource sharing, and advanced resiliency schemes, all of which are needed for true commercial quantum advantage. Even better, we deliver this in the form of an advanced integrated quantum photonics on commercial Foundry silicon, removing massive cost, risk, and time to market obstacles. And then here we see the management team, right? So the founders, which we've seen before, right? John Sullivan, and then Manish Singh, who are the CTO and the CPO, and then also the CEO, Charles Foley, as a chairman as well. And then the board of directors down here, with also co-founders, but then, I guess the board of directors with different roles as well. And then the investors mentioned down here, like Blue Capital Sky and others mentioned down here. Okay, and then again, we see this, we see a video here, and then about the team. So the memQ team. The memQ team brings deep expertise in key areas needed to develop quantum technologies. I think we've seen this text already before on the starting page, so I'm not going to go through this whole thing again. I think with that, we are already at the end of today's video. I hope you liked it. memQ definitely an interesting, let's say, part of the whole quantum ecosystem, right? Let's say, thinking about the scaling challenges, this could be another solution. I think in general, this whole optics topic is very interesting. In one of the previous videos, and if you haven't seen that one, go into the Hidden Quantum Champions playlist and look for it. I've been talking about a company that is using optics to communicate between the quantum chips or the signal processing and the outside of the cryostat as to like where the classical computing is happening. And that one is also very interesting. So there's a lot of stuff happening in the world of quantum communication, optics, and quantum chips or quantum processors. memQ is definitely also very integral part in this story. So if you haven't seen the other one, go ahead and check it out. If you like this video, make sure to give it a like. And if you get the opportunity to hype it, then of course also hype it so that more people get aware of these great quantum technology companies that we are looking at here. I'm looking forward to see you in the next video. Until then, bye-bye.